So we have seen the concrete, not the concrete. So we have seen the collection interface, which is an abstract interface which has various parts to it, and we have seen how this interface is then implemented by this abstract collection interface, which tells us how to implement many of these things by default. So now let's look at concrete collection. So collection itself captures all these groups which are not key value pairs, right? So which are not structures like dictionaries, so arrays, lists, sets and so on. And then what we can now observe is that within this there are categories, right? So lists and arrays have an order. There is a first element, a second element and so on, whereas sets are unordered. So there is a distinction between arrays and sets or lists and sets. Sets are supposed to be unique valued. You can't have two elements of the same value in the set, right? So set has only one of each type. So no duplicates are allowed. This is not the case in an array or a list. The same value could appear at multiple positions. Something like a queue has constraints on how you can add and remove. So in a set, you can add and remove anything. In a list or an array also you can add and remove, you can change a position and so on. But in a queue, you can only add at the rear and remove from the front, right? So these are all now different extra properties which all go along with the basic idea of a collection of values. So the logical thing is to capture each of these through a sub interface. So just like you have a subclass, you can have a sub interface. So there is a sub interface called list which extends collection, which talks about ordered collections, collections in which there is a sequence of values. Then set is a sub interface of collection which talks about collections without duplicates. They may or may not have an order, but the main thing is you don't have two copies of the same value in it. So the crucial thing is that sets don't have duplicates. And then for instance, we will look at one specific thing called queue, which is an ordered collection which has this constraints on insert and delete, right? So the basic queue, a vanilla queue that we have has a constraint that you can add at the back and you can remove the front, but we will see other kinds of queues also. So let's start with lists, right? So a list is a sequence, but now when we have a sequence of values, there are two ways that we can identify an element in the sequence. One is to start at the beginning and go through an iterator and reach it, right? Or we can say I want the value at position I, right? This is called random access. So in any sequence I can do this. I can start at the beginning and walk 7 steps, or I can say I want the value at position 7. So in this list interface, right, we have this extra random access functions now. So remember that the original interface of collection had an add and an iterator. So that allows us to go through the thing from beginning to end. But now that we have this notion of a position, it is meaningful to talk about the value at position I, right? So I can say add an element E at this index. So this is a different add, right? This is not the add which is there in the collection interface. This is a different add. That one just says add an element E. This one says add an element E at this position. Similarly, I can say remove a value at this position. So, shrink the sequence by removing the 7th value. I can also ask, right, this is the familiar thing that we normally write like this, right. I can say get me the value at an index, right. And similarly, I can say set this value to be something, right. So I give you the index position and I say change its value. So these are things that we do implicitly when we deal with lists and arrays, but now they are kind of changed into functions because they are in this object oriented setting, right. So we can get a value at a position, set a value at a position, we can add a value at a position, we can remove value at a position. So we now have an extra thing, which is that even the iterator can be a little bit more functional in some sense than the basic iterator. So the basic iterator has next, right, and then it says next gives us the next thing, right. Now if I have an iterator, remember that there is a notion of a position, right. So I can take a position and I can remove it. Now if I have something where I know these positions, then I can also insert something there. So there is something called a list iterator. Okay. A list iterator is something which extends the vanilla iterator that we have with collections, and what this list interface allows us is to call for a list iterator. So remember, the collection gives us a normal iterator, so we can still get a normal iterator if we want, but we can also ask for a list iterator, and a list iterator is more functional than a normal iterator. So in addition to everything the normal iterator can do, get me the next value and has a next value, right. Here I can add an element at the position before the current index. So, I am always at some index, right, in a list iterator or any iterator. So, you can remove that, and I can go backwards because there is a sequence now. Right. So, as we said, an iterator just goes through all the elements in a collection. If there is no natural order in that collection, I still have to be able to go through all through, but there may not be a meaningful way to go back to the previous one, because maybe the order in which it's generated doesn't keep track of which order so I don't keep track of what I have seen before in any particular order. So, going backwards normally may not make sense in an iterator, but in a sequence there is always a sensible way to go back. So, a list iterator in addition to a next has a previous, and just like in a list iterator, if you try to go next after the last element, it will be a problem. So, in a going previous before the first element is a problem. So, just like has next, you have a has previous. Right? So, in this way, this list interface allows you to exploit the fact that this ordered collection has positions. So, you can make changes at fixed positions, and you can also get this more functional iterator which allows you to go forwards and backwards. So, though all this is provided, this random access in particular, getting to the ith element is provided to you by this list interface, it is not true that all versions of sequences are equally and amenable to random access. So, if you have an array, right, so an array is a picture that we saw before, which is just like this, then normally what you can do is if you give me I can calculate the position of a of I, because I know that this is the 0th position, and normally an array will have all elements of a uniform type. So, I will just have to say, okay, this is a block of storage, here is my first element, I have to skip I elements times the size of each element, and this is where the ith element will be. So, just by using arithmetic, I can figure out from the start of an array where the ith position is, right. On the other hand, if I have this usual kind of linked list as we saw, where each element points to the next, the only way I can do it is to actually traverse I links. So, it takes me time proportional to the position to reach that position. So, even though I can talk about the ith element in the linked list, it is still a meaningful concept, because the list has a beginning and an end, and it has position 0, 1, 2, 3. Getting to the ith element is no longer the same, right, in terms of efficiency. So, the functionality is the same, but the efficiency is not the same. So, what we can use is, so there is this, should be access. So, there is a tagging interface called random access. Right. So, random access is, it does not do anything, it's a special kind of interface which is there, we will see in other places also in Java. It just is a way of indicating whether a class has as a whole has a property or not, like an object has a property or not. So, we can say if C, the thing that I am dealing with, is an instance, so this collection is an instance of random access, then I can assume that random access methods are actually efficient. So, if I have designed an algorithm which wants me to go to the ith element and the jth element, say a typical example is a swap kind of thing, right. If I want to swap the ith element and the jth element in a collection, if I have random access, is very easy, because getting to the ith element, getting to the jth element takes the same amount of time, a constant amount of time, and then exchange them. So, I just reassign these two values. Whereas, if I have to go to the ith element and go to the jth element and then update them, then I have to first go through once and pick up the ith value, pick up the jth value, then I have to go back again and then go back to the ith value and put the value that I found at position j and so on. So, I have to actually go around and around this list more than once, right. So, I can choose a strategy by looking up this tagging interface called random access. So, that is one way of getting around this problem, that the list interface as such provides you random access without any promise that the underlying implementation, remember, list is still an interface, it is only telling you capabilities. So, as anything which is an actual object which implements or extends this interface list will have the capability of going to the ith element. Now, whether it is a meaningful and efficient thing to do with that data structure or not, you can find out at runtime through this random access. So, remember, we said that collection as it stands is not very usable, because it has this whole zoo of abstract functions which need to be implemented, and it will be a real tedious task to implement all of them. So, instead Java created this intermediate abstract class called abstract collection, which sits below collection and provides default implementations for many things. So, in a similar way, the list interface that we talked about is a sub interface of the original collection, but there is a corresponding version of the list interface which is called abstract list, which sits under abstract collection. And this abstract list will have all the default implementations that come from abstract collection, right. So, abstract list will inherit everything that abstract collection does, but it will also have all the extra interface capabilities that list has. So, it is a kind of a merge of the two. And then within this, there is this notion of random access and not random access, right. So, we have a further subclass or abstract class called abstract sequential list, which extends this abstract list class, and this is for list implementations that do not support random access. So, if you look at concrete classes that are available in Java itself, these are not things that we have to write. So, there is something called a linked list, right. So, linked list is exactly what you would expect. It is something that implements this, except that you do not have to worry about the implementation, right. So, normally when we write in a programming kind of course, we are asked to implement a linked list. It's our job to keep track of these nodes and all that. This is something which is provided to us. So, Java has provided us a linked list. It keeps track of the nodes. We don't have to worry about it, and it has all the functionality that we get with the interface. So, we can traverse it using an iterator, we can get a list iterator, we can go backwards, forwards, all that. So, at a high level, it is just like any other list. The fact that it is implemented as a linked list is just information for us to know how to use it effectively, right. So, whether or not it is an efficient thing to use or not. So, internally it is just a usual flexible linked list. So, in a linked list, the usual thing that is good is if I want to remove this element, then it is relatively easy. I just have to do some plumbing, right. If I want to insert an element here, I just have to change again this link and do it. So, inserting and deleting and modifying a list in the middle is relatively inexpensive with a linked list. But what is expensive with a linked list is getting to a particular position, right. If I want to go to the ith position, I have to walk there. So, there is a trade off between flexibility and this random access. Similarly, there is something called an array list. So, an array list is essentially an array, except that its size is not fixed. So, when we write a Java array, we have to say this is an array of size something, right. An array list, we do not have to fix the size, we just say this is an array list of a particular type, and it will just keep growing as needed, right. So, it is a flexible size array, but the advantage is it supports, so underlying it is an array. So, actually the lists that we see in Python are actually array lists, right. So, in Python when we say L is equal to whatever 0, 1, 2, right, it is not that Python is creating a list with exactly 3 elements. What Python does is it actually gives us a large block of storage which is an array, and it uses a small part of it. And then if our list actually exceeds this, then it goes ahead and says, okay, this is not good. So, it gives me a double size storage and say henceforth work with this. So, as the list expands in size, the array allocated will change and I will get a bigger array, but at any given point I am actually working within an array. So, random access is possible. Okay, so, that is how Python lists work, and that is how an array list works. So, this concrete class, as we said, linked list, extends as abstract sequential list, and therefore, it is not a random access class. But remember that this is only a kind of limitation from the point of view of efficiency, right. The random access methods are still available. You are not prevented from using random access methods because that is part of the list interface. So, for instance, you could well write a loop like this, right. You can say for I equal to 1 and up to the list of the size, get the ith value, right. So, this is remember that get is this function. And what will this do actually? It is kind of strange. Normally when you are doing something like this, if you are doing it by hand for instance, you would actually go through this list once, right. So, you will go to the 0th element. So, you could actually write a loop like this to go through a list manually efficiently by going through it once. But because we are using this kind of get operation, what will happen here is that each time I call get, it will start again from the beginning and try to go to the ith one. So, it will try to simulate this random access. So, it is not remembering where it was, it does not know that it was at I minus 1 at the previous step, right. It just goes back and from scratch it goes from 0 to I. So, this is horrendously slow, right, but it is not forbidden. So, this is something that you keep in mind. So, the fact that these things are known to be sequential lists does not forbid you from using the random access functions in lists. So, it is up to you as a programmer to make sure that you are not using the wrong function on a particular data structure. The other thing to keep in mind is that we have sometimes multiple versions of similar looking functions, right. So, we have this add function which is available at the level of the collection, right. We can provide a new element to a collection as a whole. We also said that the list iterator allows us to add a value or insert a value rather before the current position of the list, right. So, this is not there in the normal iterator. The normal iterator allowed a remove, but this is allowing us an add. So this is a different add from the add which is available in collection. So the add which is available in collection is like an append, right? It will add at the end of the list. The add which is available in the iterator is actually an insert. It will insert at the current position. There is also a difference in the signature, right? The collection add returns a boolean. You might wonder, why should it return a boolean? Well, it returns a boolean because in certain collections add may not work. Remember that we said that a set has no duplicates. So if I try to add a value v to a set and the value v is already present in the set, then add has no effect. So really this add reports to you whether the set changed or not, whether the collection changed or not. Now of course in the context of a set this may or may not happen. In the context of a list it will always happen. So if I use this collection version of add for a list, I will always get a response true. If I use it for a set, I may or may not get the response true. So this is the version of add which is there in collection, right? It adds at the end. The version of add which is there in the iterator doesn't have to worry about sets because it is not something which is associated with unordered collections or with collections without duplicates. It's specific to these ordered collections where duplicates are allowed. So insert will always work in this case, right? So therefore there is no need to signal whether it is true or false. So therefore the add in the list iterator actually returns a void. So they actually have different signatures, but it is just important to remember that when you are dealing with a list, right, don't accidentally, because they occur in two different contexts. You must explicitly create an iterator and use that add to get this insert operation. Whereas if I just have a list L and I say L dot add, I will end up using the collection one which appends at the end. So it's important to be aware of these subtle differences between the different versions of the function which have similar names in this thing. So let's move from ordered collections to unordered collections. So we have something called a set. So like list, set in itself is an interface, and what set guarantees you is a collection without duplicates. So set has, unlike list, set, so remember list added something to the collection interface, right? It added these random access things which allowed you to add, get things at particular values, set things at particular positions, so on. So a set does not have any other things. So the interface of set is actually the same as the interface of collection, right? So the only thing is that the behavior of the functions is constrained. So in a set, right, add should have no effect and it should return false. Equals should return true if the collection as a whole is the same, even though there might be differences in order. So we have more constraints, and you might ask, what is the point of having two interfaces the same signature? It is so that as a programmer, right, you can insist that an argument to a particular function must be a set and not an arbitrary collection, right? So it allows you to constrain the type to behave within constraints which you can then assume in the code that you are writing. So you know that when something passes this set type declaration in your function, that you can operate on it as though it is a set. So that's the reason why it's important to keep these two named differently, even though they look superficially, they will have the same functions available to them. So the principal difference between implementing a set, you could of course implement a set inefficiently by just calling it a collection of ordered size, and every time you want to insert, you could just walk through the entire collection and see if the value is there, and if it is not there, add it. If it is there, do not add it, right? So there is no problem implementing a set using a list or an array. But the difficulty is that this is not the intention, right? The intention of a set is that you want to quickly check whether something is there or not. So a set is really used to keep track of a collection of things and add things if it's not there and remove things if it's there, and so on. So we have, as we said, if you have an ordered collection, the only way to do this is actually cycle through the entire collection. You have to do a kind of iterator type of thing, or you have to go through the whole thing. Of course, if it is, has some other properties like it is sorted, and if it is a random access thing, maybe you can use binary search to find it. You can halve you can look for the midpoint and the midpoint and so on. But still, it requires some work to do it. Whereas in a set, you would like to do it upfront. So usually, the way that a set would do this is it will have some underlying storage, okay. So every piece of data in your set is stored somewhere. What you want is a way to take the value that is being stored and map it to that position. You want to say, oh, if the value is 7, it must be here. If the value is 22, it must be there, right? And this is something which is done by applying a function, a mathematical function to the value to give you a number, and that number tells you where the storage is, and this is something which is usually called a hash function, which we will not talk about too much here. The other way to do this is to arrange it in a nice data structure. So there is something called a search tree where you arrange things cleverly so that you can basically find things fast, right. So this is the equivalent of what I was talking about earlier. If you have a sorted sequence, like if you have a, say if you take a sequence like a normal dictionary, not the Python dictionary, but an English language dictionary. If you are searching for a word, the words are in alphabetical order. So if you can look at the word that you are looking for, you can easily decide whether it's going to be in the middle, the beginning, or the end. And if you open the dictionary at a page at random and you look at the words on that page, you know whether the word you are searching for is before or after, right. So in a very short amount of time, you can zero in on the page where the word is. So the same way, you can kind of use this balanced search tree in order to look for a value quickly. So as usual, we have this set which is an interface under collection, and it has all the abstract functions that collection defines, and we said it has exactly the same things. And then we will have a corresponding version called abstract set, which inherits all the default implementations from abstract collection. So when we actually provide a concrete data structure which implements this set interface, it will be actually an extension of the abstract set and not this set, right. So what are the concrete things? Well, there is something called a hash set, right. So hash set is what we were talking about. It's something which implements this idea of a hash table. So a hash table is basically, I start with an array which has some position, some 0 to n minus 1, right, and then some value comes. So I compute some h of v, and this gives me some k. So this function can be something, it could, I mean, just a simple thing, it could just be, if it's a string, it could be, for example, if I take the bits in the string and I just think of it as a binary number and then I do modulo n or something like that, right. So it's some function we are not worried about. The design of this function is important for this data structure to work well, but let's not worry about it. Abstractly, it gives you a k, so I go to position k and I put my v here. Now this is fine, except that now I give you another. So remember that this is a finite thing, right, 0 to n minus 1, and there might be an arbitrarily large range of values which come. So more than one value will have to be mapped to the same thing, because I cannot have storage which is equal to all the strings in the universe, for example. That would be impossible. So now another v prime comes, and it happens that h of v prime is also equal to k, right. So I go to the same k and I find that there is already a v there. Then I have to do something, right. So one possibility is I go down and I say, okay, is the next slot free, and then if I use that and I put v prime here. So these are, so this is called a collision, and there are many different strategies to deal with collisions, right. So if you have done the data structures course, you would have seen it. If you have not, when you do data structures, you will see it. But basically this is a standard thing. So there is a hash table. So a hash set essentially uses a hash table to store for what we are concerned about is that finally you get a set implementation out of it. So to check whether an element is a member of a set, you hash it and see whether that position is there or not, right. So checking membership is fast. You just check whether v is at hv modulo this collision and looking for it elsewhere. So this is unordered. There is no particular sequence. As we said, this hash function kind of scrambles the values according to that thing. So there is no such thing as the first element in the set and the last element in the set and so on. But of course, the notion of an iterator still makes sense. So if I ask for, because it's a collection after all, so it must support an iterator. So if I ask for an iterator and I start somewhere, what will essentially happen is that I will get all the elements in a set in some unspecified order. So I cannot predict the order in which they will come, but I am guaranteed that if I start with a fresh iterator and I keep saying until as long as has next is true, I keep getting next, and I keep going until has next becomes false. If I run through that usual while loop involving, or if I say for something element x colon s, right. If I do any of these standard things that we do with an iterator, I am guaranteed that I will visit every element in that set exactly once. So in that sense, I will loop through the set, but not in any fixed order. So the iterator still makes sense to examine all the elements in the set, even though it does not have any fixed order. So we said that hash set is one thing. We also talked about the search trees. So there is another tree set, which is a tree representation. So one assumption that we need when we do a tree representation is the values in our set can actually be compared. I can say this value is bigger than that value, that bigger. So really what happens is that this tree set maintains a sorted collection, and since it is sorted, actually we have extra structure because we have a smallest element with respect to the sorted order and largest element. So, actually in such a situation, unlike in the hash set, the iterator actually will go through the values in sorted order. So, we have an extra guarantee. So, again you may not need to worry at the level of set whether you're using a hash set or a tree set, but tree set has more functionality. So, if you need this, then you can use it, but it comes with a price, okay, which is that maintaining a tree is more complicated than maintaining a hash table. So, each entry insert and delete will take time proportional to the log of the number. So, you pay a price on one side and you gain a benefit on the other side. You have an ordered iterator, but you pay more for each insert into this tree. So, finally, let us look at this queue. So, remember a queue is an ordered sequence in which you insert at the back and you remove from the front, okay. So, this would be a queue interface, right. So, it has this add and remove, and now a queue will typically have a bound. So, add may not always be possible. So, if the queue is full, right, if the queue may not have a bound, it might be a linked list, in which case the queue will always allow you to add. But if there is a size limitation in the queue, like you have implemented a queue in an array, for example, and you run out of space, then add will actually flag an error. We have not talked about errors in Java, we will do that probably soon in the next week or so, but you will formally get an error saying that you tried to add to a queue which had no space. More importantly, if you try to remove an element from a queue which is empty, that is also an error because there is nothing to remove, right. So, these are the things that happen when you use add and remove. So, what queue does is it gives you a kind of gentler way of doing this. It has the same functionality. So, instead of saying add, you can say offer, and instead of saying remove, you can say poll. So, if they work, it works the same way. So, offer is the same as add, remove is the same as poll, provided the operation succeeds. If the operation fails, on the other hand, instead of getting a Java error which you have to handle through this some error handling thing, you will get a value. So, here if I try to add and it fails to add, then the add will return a boolean. If it is true, it means the add succeeded. If it's false, it means the add failed. Similarly, if I poll and there is nothing in the queue, instead of getting an error, I will get a null. So, if I get back nothing from my poll, then I know that there was nothing there. And there is also a way of inspecting the head of the queue without removing it. So, you just want to see what is the first element in the queue, right. So, this should be, I think, peak. So, there is something called element which will look at the first element, but again will throw an error, and there is something called peak which will look at that first element, and if it is not there, if there is nothing there, it will return a null. So, this is the basic queue interface. So, this is again an interface, not an implementation. Now, we also talked about, when we were discussing this difference between subtyping and inheritance, we talked about this thing called a double-ended queue. So, double-ended queue allows these things to happen at both ends, right. You can have a insert at the beginning, insert at the end. So, you take all these functions. So, you take add and you make an add first, add last. You take an offer and you make an offer first, offer last. So, beginning and end. Poll, you can do a poll first, poll last. And then here, instead of element, right, it is called get. So, you have a get first, get last, and remember that this was peak, alright, you have a peak first and peak last. So, it is essentially a double-ended version of the interface of queue. So, you can do this thing at both ends. And then there is another type of a queue which is called a priority queue. So, essentially in a normal queue, the priority is in order of arrival, right. So, the thing that arrived first has the highest priority. So, people are served in a normal queue, like you go to a shop or some kind of place, right. People are served in the order in which you arrived. But what if you had a kind of service, right, where people who pay more get served first. So, people have different types of tickets. So, they buy, and now if they have a ticket for which you have paid more, you jump the queue. So, you have a priority. So, this is called a priority queue. So, in a priority queue, remove will remove not the earliest value that came, which is what you will get in a normal queue, but the highest priority, right. So, each element in the queue, they will have a value associated with it, but will also have a priority, and you will choose according to that, right. So, these are all different types of queues, and these are all interfaces, right. And concretely, you can use some very basic data structures, like a linked list is implicitly a queue, right. When you insert at the tail, and when you remove from the head. So a linked list on its own with just the add and the normal add operation at the end and the remove the first thing becomes a queue. You can take the circular array that we talked about earlier for queue and you can have a same interpretation for a deck, right? So you remember the beginning and the end, and then you can insert and delete at both ends rather than just inserting at one end, deleting at another end. So there is a built-in type in Java called array deck. So this is not exhaustive by any means. So you should look at the Java documentation, and if you are trying to look for a particular data structure, if you know about a data structure which is useful for you, very likely there is an implementation already in Java. So make sure that you check before you try to implement a new data structure, because that is one of the nice things about Java, is that a large collection of standard data structures which are defined in data structures textbooks and so on are actually already available as implementations, and they all fit into this collection hierarchy. So that is something that you should keep in mind, right? So you should try to understand how these interfaces are all organized so that there is a natural, I mean, it is a bit like the way that we biologists try to group species, right? So it's a bit like all these things have been classified. There's what's called a taxonomy of these collections, and they're all fitted into a tree so that they all sit in their appropriate place according to their capabilities, right? So to summarize, we have these different types of collections which are defined by sub interfaces. So ordered collections are of type list. Unordered but without duplicates are of type set, not necessarily unordered but certainly without duplicates, and those which have this restricted insert delete are under queue. So list will allow random access and it has a more functional list at iterator. Set will ensure that there are no duplicates. Queue will support this restricted add and remove, and all of these are actually implemented by having a corresponding interface or abstract class rather, which is under abstract collection, right? So they will have a corresponding version under abstract collection which implements many of the default methods for the large number of methods which are there in collection, right? So the concrete implementations will extend this abstract list, abstract set and abstract queue.